Welcome to all on-site and online. Great to see you for the talk today of Professor Stensrud. Mats is a tenure track assistant professor at the chair of biostatistics at EPFL. His talk today is titled On Optimal Treatment Regimes Assisted by Algorithms. As always, we have 1 hour. I think, Mats, you planned for 45 minutes.
Yep.
And he even agreed to take your questions online. So you don't have to wait until the end. Feel free to put them in the chat or raise your virtual hand if you have anything urgent to be addressed before the end of the talk. I'd like to thank the team for organizing this event today. And of course, Mats, thanks, and the floor is all yours.
Thank you very much, Jan, and good to have you in the Zoom room and also here in the actual room. I will jump right into it. And what I will start with is precision medicine. So precision medicine is all over the place, at least in my domain. I work in statistics, and there's a lot about this, and in particular in medicine, which is my other camp. And what people often associate with precision medicine is a lot of data and omics, proteomics, genomics, and all kind of clinical measurements that they have of the patients. Okay, that's fine. But what I think about when I think about precision medicine is actually making better decisions for the individual patients. And I think I can back that up in some way. So in 2015, in his State of the Union address, the yearly speech for the American Congress, Obama launched a precision medicine initiative, which meant that he allocated hundreds of millions of dollars to research and clinical implementation of precision medicine initiatives. And his quote, the way he motivated this, is that doctors have always recognized that every patient is unique, and doctors have always tried to tailor their treatments as best as they can to individuals. And this was the premier, his phrase for saying that, and now we need to pursue this even more with access to all the new data and technologies we have. Okay, but the core is quite easy. It's about how can we tailor decisions to patients' characteristics that we somehow measure, possibly with new technology. Okay, and of course, there's a lot of work on actually using the new technology in order to get better information that in turn can be used to make the decisions. But what I will talk about today is more how can we actually sensibly use the information we have and get theoretical guarantees for how we can use this information to make better decisions. And the premise is also quite simple. So people are different. There's heterogeneity. And we want to leverage that heterogeneity or those differences in order to make individualized decisions. I say individualized and not individual, and we'll get back to that. And I would also emphasize that when we make decisions, there exists already a lot of theoretical work on how we can do that, so how we can make these decisions in a sound and at least coherent way, using principles from decision theory and also from causal inference. And why is this a causal inference problem? Because say we face a very simple binary problem. So I go to a doctor, they find a disease, and I have a choice between either taking the treatment they offer me or not. That's a binary decision. And my choice of treatment is, I would argue, usually based on my sense that whether I take treatment A or whether I take A equals 1 or A equals 0 would lead to the best expected outcome. So what would happen if, and a what would happen if question is a causal question. What would happen if I take treatment 1 or 0? Okay, so these simple decision problems are all over the place in the machine learning literature and the clinical literature. Here I just made an example from the statistical literature, where there recently was a special issue in JASA, one of the premier statistical journals, about how to foster, and they also had many case studies on how to implement precision medicine or develop methods for precision medicine initiatives. So behind this idea of precision medicine, there's also some ideas about algorithmatizing decisions. So in this case, first we want the decisions to be based on evidence, based on data, which also means that the decisions somehow are driven by some computer algorithm rather than only the human intuition. Okay, so, but even if they might be algorithmatized, or we might have recommendation systems that says or predicts that a particular treatment is better than the other, they would usually be implemented under the supervision of humans. At least that is the case at this moment in time. And if you go to a hospital, and I think I can say this with credibility because I talk to them every now and then, they would often have some skepticism about whether the algorithmic recommendations are better than the decisions they can make themselves, just as pure doctors. Okay, so do they have any reasons for thinking this? Well, one thing is that they, as human care providers, may have a lot of information that's never been encoded in any registry, in any data set that nobody else have access to. And if they use that information to make decisions, they have access to information that the algorithms don't have access to. But that also leads to another type of problem. So if the doctor really has access to information that's not in our data, and that access also predicts the outcomes of the individual patients, then there is unmeasured confounding in the data, something causing the doctor's action, but also causing the individual's outcome. And if there is unmeasured confounding in the data, we know that actually identifying causal effects is difficult, and sometimes, if not impossible, it requires great care. And this raises obvious question: can we even know when we should let the humans override the algorithms, or vice versa, or can we even study this problem? So in this talk, I would try to touch a bit on that question. And before I dig into this, I would just want us to be on the same page about why I think causal inference is required to study this problem, even if causal inference you often would hear relies on strong assumption. And the fact is clear, because the question about what treatment I want to take, as I've already alluded to, is a causal question. What would happen if I take treatment 1 or 0? And without being explicit about the fact that this is a causal question, we cannot even know if we have reasonably identified or estimated the parameter that corresponds to our question. And the fact that there is unmeasured confounding, which may make it difficult for us to study and to identify this causal parameter of interest, does not mean that we can just escape the problem. Even if we cannot identify it with conventional methods, we might need to come up with some other types of methods that may allow us to get close or actual to identification. And if we cannot get to a point identification, that is, we cannot uniquely express the parameter we are interested in as a function of observable data, we might still be able to come up with some bounds, some inequalities, and in turn use those inequalities to make better decisions. So this is I'm presenting it loosely here now, but this is a coherent framework of thinking about such problems. And regardless of these things, I think being transparent about what the question is necessary when we are to really defend our choices to real decision makers and to real agents that have to do things that matter. Okay, so this was a bit of informal introduction. Now I'll try to be slightly more precise. And since we are doing causal inference, I talked about assumptions, which means that we need to have some model about how the world is, making some fundamental assumptions about how variables are related. And those assumptions are distinct from the data at hand, what we just observed. And we need to make those distinctions pretty clear. But we want also to use the data we observe to say something about what would happen under different policies. So what could potentially happen, that's why we call them potential outcomes, or counterfactual outcomes is another synonym. Okay, so suppose we have a very simple data structure to start with. We have a binary treatment. So this is what we might decide to do, either take it or not. And we also observe a lot of other things. So suppose we have a high dimensional vector of covariates that we measure that might guide the treatment decision we make. And we want to optimize some outcome. Okay, and just to make it simple, suppose larger values of y are desirable. We also suppose that we have IID observations of these variables. So I just omit the y subscript and keep the notation quite simple. And in addition to these observed covariates, suppose we will introduce some counterfactuals or potential outcomes. So when I use a superscript, it's not an exponent. That just is an indicator that this is a random variable under a regime. So under a treatment rule that might differ from the one that was used in the data at hand. So YG is the outcome of an individual under a regime or a decision rule that assigns the treatment to a value 0 and 1 as a function of the observed covariates and possibly also something else in this setting. So a particular case of this is the regime A, which deterministically assigns everybody the treatment, little a. So either no treatment or treatment. And I go slowly through this notation because I'll make a point about it. So I also use this plus symbol, and this is notation from in my microsphere, a famous paper called the SWIG paper, where A with a superscript G plus means the value that is actually assigned under the regime. Whereas there also exists a natural value, A only G, which is the treatment an individual naturally would take before it being forced by the treatment regime. Okay, I'll make this concrete, but the definition is this. The natural value is the value of treatment that an individual themselves would take before it's assigned to them by anybody else. Okay, so let's be concrete about that. Suppose I go to the tube and suppose they, to some patients, assign a drug A for to patients with COVID-19 that were in the hospital, say in a usual overnight unit. And suppose A equals 1 is the drug and A equals 0 is not. And in that tube where they didn't do any interventions, individuals follows their intentions. So they did exactly what their natural value told them to do. So what we observe is what the doctor and patient together decided to give. But we could imagine a value AG plus of the treatment, which is another possibly different value of the treatment that the investigator could fix and say, you have to take this particular treatment, which may be a potentially different from what actually happened. Okay, so for example, among those people who actually took treatment, I could give them a value AG plus. The regime could give them a different value and say, no, you should actually not take the treatment. Okay, so this sounds pretty clear, and or if it's not clear, it doesn't sound very deep, and it is not deep at this moment, but it will be useful. Okay, and I also want to just make one additional comment. So some people would not even be easy about defining these counterfactuals. So having random variables that exist in some counterfactual world, they find that that's at odds with the reality we are living in. And in fact, I could do all of this without counterfactuals. It just gives me a formalization for studying all of these concepts. So if you don't want to use them, we could discuss that later, and I could do all the same things. Okay, so now I've just introduced notation and given some motivation. Let's try to be a bit more explicit about what this decision-making problem is. So I said it was a causal problem, and I said, and if I were almighty and I knew my outcome had I taken no treatment, and I also knew the outcome had I taken treatment, the choice would be easy. I would just choose the treatment that maximized my outcome. Okay. So that should be an easy case. But the fundamental problem of causal inference is that I never observe these outcomes. In fact, at the time I do the decision, I don't observe any of them. And after I take the decision, I would observe at most one of them, which is the one corresponding to the treatment I actually took. So making actual individualized decisions where you really know the outcomes of interest, that's something we cannot do if our models are reasonable. Okay. So the solution is kind of clear in the sense that we need to optimize with respect to a different parameter, and using just decision theory 101, given our measured covariates, so a vector of covariates L, we could choose the regime that maximizes the expected counterfactual outcome given our covariates. That seems to be a classical decision theoretic approach to this problem. And it's a marginal quantity, and it's easily identified with standard techniques. Okay? But now I'll also define a superoptimal regime. And this is precisely the reason why I put so much emphasis on the difference between the observed treatment A, where I had a G, but it turned out that this one in an observational study is equal to A, and the variable AG plus, which is a treatment assigned by an algorithm or by some regime. And a superoptimal regime is not only maximizing with respect to the measured covariates, but also with respect to the natural value of treatment. Okay? So let me try to give some intuition to this. So the study I will use is a study by David Card. He won the Nobel Prize in economics in 2021, partly because of this work and related stuff on instrumental variables in causal inference. And one of his data sets, so he was an economist doing applied statistics and economics. And one of his key data sets was the following. He wanted to know, would a certain group of students be better off starting college education or not? And his objective function was future earnings, okay? Like economists sometimes have. And he couldn't just naively study the association between actually going to college and look at future earnings because it's massively confounded. Those who go to college, they usually have more resources already. They may have better skills. They have come from families or cultures where people are academics. They meet people and so forth. So it seems not easy to measure all of these factors. But these economists, they tried to come up with clever strategies for even in the presence of unmeasured confounding, come up with strategies to identify causal effects. So what they used was the distance to the closest community college. So a community college here, they were studying people not from the best high schools, and they looked at the distance to the closest community college. And the intuition was that if you, for some reason, and their implicit hypothesis is that those distance are more or less random, live closer or further away from a community college, that might affect your probability of actually taking education at that college. In particular, those being very close by might be more likely just to take the education because they're influenced by this environment, regardless of their other skills. And we might discuss whether or not that's a plausible assumption, but that was part of the Nobel Prize winning work. And this is a data set they've used over and over again. Okay, and later on, this data set have also been used to trying to figure out when should a student start college education? So how could we use measurements about the student, such as their age, cultural background, the education of their parents, IQ measurements, and so forth, in order to give them a tailored recommendation. Yeah, we can do that. And people did that, for example, in this special issue of JASA that I previously mentioned. But when I introduced these superoptimal regimes, there's like one additional question you could feasibly ask as another covariate that seems quite obvious. You ask the student or prospective student, do you intend to take college education? And then you feed in the response to this question to the algorithm, and it shouldn't be. So I'll go back to the previous slide, which means that you optimize the decision also based on what their natural choice would be, what they would have done themselves. Okay, this sounds quite obvious. It's just an additional covariate. But the funny thing is that that hasn't been used in these kind of problems. And we will see later on, and some of you who are used to decision tree may see it already, is that these superoptimal regimes are guaranteed to be as good or better than the optimal regimes. And that follows from decision theory, because if you use more information, you have more access to more variables. You cannot do worse than when you had less variables in expectation. Okay. So we may also be a bit uneasy about this kind of reasoning from a more philosophical point of view. So suppose I know also views the student's intention, or it could be a doctor's intended treatment, or what the patient themselves want to take. And suppose then I come up with a decision rule that says you should do exactly the opposite of what you say. Sorry. So you ask them, and then you come up with a decision saying, sorry, no. Since you said that, I'll give you exactly the opposite. That's perfectly possible with this kind of algorithmic type of decision making. I'll get back to how that's not different from things that's done at the moment either, but we may feel somehow uncomfortable with that. And I agree with that. But the literature is rife of examples where actually people have done exactly the opposite of what they should do. So here's one example. I wouldn't be able to guess who this person was had it not been for the fact that I actually found the picture. This is Semmelweis, who was who is a famous figure in medicine, and at his time became a very famous person in Europe because he discovered the following. So he was a doctor in Budapest, and he saw that a lot of young women who came in with obstetric problems, so they were about to have a newborn, who went to the best hospitals in Budapest and came from the best conditions, suffered from perpetual fever, so an infectious disease just after having the obstetric treatment. And they couldn't figure out the clear reason for that, but it seems like all of those people where the doctor says you should actually go to the hospital and get care for this, they really came out with a serious infectious disease afterwards. And later on, so he discovered this, but later on they figured out that that was due to hygiene problems. Like they didn't really clean the equipment and particularly their hands well between the patients they were doing a surgery on. So his recommendation to this woman was to exactly not go to the hospital if the doctor tells you to do this. So this is something that can happen in practice, okay? I'm not saying that this is a defense for doing it in practice, but knowing, so using this algorithm to figuring out when the automatic decision is precisely the opposite of what the intuitive or the doctor's or the patient's decision is, that's information that should be useful for us and should be used by us to take one step back and figuring out what's going on. And I also want to make a distinction between what's going on in a lot of the intersection between AI readings of images and decision-making in clinical medicine, where in a lot of cases, doctors who in the old days did, like on the left-hand side here, had to look at, say, pathological specimens like this one and figuring out what the diagnosis is and then subsequently do decisions. Now they can get help by algorithms to focus on suspicious parts of the specimen where there might be something and thereby have an augmented image, which is easier to analyze. But this is very different from what we are doing here in the sense that we are asking the doctor first to make their decisions independently, and then we feed the doctor's independent decision to an algorithm, and then we let the algorithm come up with their recommendation, which in turn can be used by the doctors to make a decision. Okay. So a lot of the work I do usually involves graphical structures, and this is a fairly simple causal directed acyclic graph. And this graph illustrates a common causal structure where we have an instrumental variable. So this C could be this distance to a college, which is an instrument in this economic example I had before. And we also have a treatment A that we want to study, but there are some unmeasured common causes of U and Y. So this is the unmeasured common causes, the unmeasured confounders. For example, it could be all these factors we don't measure about the individuals that could predict their future earnings, but also predicted whether or not they went to college, or they could be all this information doctors have that were never recorded in any registry, but the doctor used to make decisions, but also predicted the future outcomes of the patient. Okay? But there's a problem by just using causal graphs in the sense that, and I think that's the reason why people haven't really used all these variables I'm interested in these problems, is that the distinction between the natural treatment value A and the treatment value that we want to assign, which could be different from the natural value, they don't appear both on the graph. And that's why we can go back to SWIG, so single world intervention graphs. These are also directed acyclic graphs, but they have a particular causal interpretation. And there's a beautiful theory in this graph developed by Richard and Robbins in 2013. Here we'll just use them more as an illustrative tool, where in this case, we can depict how under the regime G, so a new decision rule, that could be a function of the observed or natural treatment value A, but also other covariates, how we can use that to identify causal effect. Okay. So I said this already in words. I said that the superoptimal regime, GSUP, is always better than an optimal regime. Okay. And that's a 3-line basic probability proof. It's not at all surprising, and people have done similar things before. But that fact in itself is fine, but it's not very interesting if we were not able to actually identify or study the superoptimal regime, or if we were not able to study the superoptimal regime in at least most of the settings where we also can study or identify the optimal regimes. And that's why the task of identification, and I'll be clear about what I mean about identification because people mean different things, but in this case, causal identification, what I talk about is how, or we say that the parameter is identified under a collection of assumptions if we can express it uniquely as a law of the observed variables. So I want to be able to express this right-hand side uniquely as a function of observed covariates, not only the left-hand side. Okay, so importantly, and this is why this can be useful in practice, is that if I somehow can identify, so express this quantity as a function of observed variables, which is a special case of the optimal regimes, because it's just really the regime where everybody gets one treatment, either 0 and 1. Then I can also identify the superoptimal regime, which means that to get these value functions, so to get these conditional means, under either the superoptimal or the optimal regime requires, in many settings, the same assumptions. And that has some consequences in the sense that if I go back to some of these recent papers, we can then, just by these very simple results we have already, we can say that in some of these papers, they have just studied usual optimal regimes. We can take exactly the same results they have, and we can just by this simple argument say that if they further study these superoptimal regimes, we can guarantee that they will get to better decisions in expectation without adding extra assumptions. Okay, so this happens because of a very simple lemma. I'm not going to go through the details here, but this is also a quite simple result that happens if people are very into this kind of field. It's very closely related to something called treatment effects in the treated. Okay. And I should also say that similar ideas have appeared in different literatures. So, for example, in the bandit literature, there's recently been some interest in similar things in experiments. And the realization they have had in that literature is that actually, it's not clear that by doing an experiment and trying to figure out what is the best treatment strategy or experimental strategy to optimize some kind of objective function of interest, it's not always clear that we can find that in the experiment. That is, it's not always clear that the experiment will give us anything better than what we already had in the observational data when people can do whatever they want, because we don't have the access to their expert knowledge. So they come up with ideas about how to, in the experiment, also use the expert knowledge at the same time. But the difference from our setting is that we are not only interested in doing this in experiments. I also want to do this when we have data sets, say, from a hospital, or say from this economic study on the effect of education on earnings, where you don't even have access to experimental data at all, in an offline setting, say, where we just have data and we want to make certain assumptions. Okay. Here's another somehow important result, is that, and it's not difficult to show, but this superoptimal regime, where you further use the individual's desired treatment or the doctor's suggested treatment, is equal to the classical optimal regimes whenever the following independence holds. So this independence is saying essentially no unmeasured confounding. So no unmeasured common causes of treatment and the outcome, the counterfactual outcome. So that's essentially no unmeasured common cause and no unmeasured confounding. So this has some implications, because if you somehow can say that the superoptimal regime is better than the optimal regime, then there must be unmeasured confounding. Otherwise, they should be equal. Okay? Which means that if you can say that, you know that the decision maker had access to some information that was better than what you had in the data. So in that sense, then you have then the doctor has an argument. They can say, you know what, we can do better than your algorithm. And you also know that if you somehow can tease out what that information is, you can make your algorithm better. Okay? And I'm not going through the theory here, but there's some nice new results on graphical models saying that, in fact, if you not only have access to their intended decision, but also the variables they had used to make that intended decision, you would make even better decisions. Okay? So this is important because if we then have access to augmented information from an observational study or somewhere where the treatment was not in experimental controlled settings, we can actually get better regimes. And we can stretch the bar quite a lot and say that if we have identification, so if we can figure out what causal effects are in observational studies, then having those data might be even better than having experimental data, because they can allow us to identify superoptimal but not optimal regimes. But there's a massive but here, because identification in observational data is so much more difficult than in an experiment. That's why we do all of these experiments. Okay, so far I haven't given any concrete examples about the utility, except alluding to this David Card example on future earnings. So let's be a bit more precise. So I go back to this exact same graph. So the graphical structure will be exactly the same. And I will use now an example from the medical literature. So the question is, here we have a group of patients, or here we actually have an individual patient with certain characteristics. They come to the hospital, and the doctor has to decide, should this patient be admitted immediately to an intensive care unit, an ICU. So let A indicate what I say is immediate, which means within 4 hours be admitted to an ICU unit. And again, we know that if we just have observational data like we had here from a large British healthcare system, the NHS, we know that those patients who were admitted to the intensive care unit, they were probably much more ill than those who weren't. So there's probably massive confounding here in the doctor's decision of giving intensive care to a patient versus not doing it. We can try to measure some of these reasons, for example, their age, certain clinical scores, such as the SOFA score, which is a scale from 0 to 15, where they measure. Actually, I'm not even sure if it's 15, but a scale to 0 to n, where they measure the symptoms of the patients and other clinical characteristics. But still, that would likely not suffice to actually have no unmeasured confounding. But in addition, the guys who studied these data sets before were kind of clever in the sense that they say, well, there's another factor, which is unrelated to this doctor's symptoms, is how many people are already in the intensive care unit. So if there are a lot of people in the intensive care unit, you would expect that the doctor is more strict on the admission. If there are not a lot of patients in the intensive care unit, you would expect them to be more liberal. So you can use that as an instrument in the same way. And suppose the outcome is survival. So people have tried to figure out what's the optimal strategy before. Now we can do it with superoptimal regime. And I took this as a illustrative example because it's an example one of my students is running right now. So I can't give you confidence intervals, which of course I should if I'm a serious statistician, but the bootstrap code is running. So this came this morning, and we could say that, and we should take it with a grain of salt in the sense that this is more of a applied example more than a full-bodied clinical examination. But using these methods, we would predict that the overall survival in the ICU would be 83% instead of 81% if you adapted this new superoptimal decision rule. So 2% higher survival, essentially, which might matter. Okay, so this is just to give you an illustration that using these new concept of what is an optimal regime may actually objectively increase or improve clinical outcomes. So earlier in this talk, I also mentioned bounds. I did it very briefly, and I said, if you cannot point identify, so you cannot uniquely express the parameter of interest as something you can study with data, you might still be able to bound it. And these results could also be quite interestingly applied in settings where people have been happy before with bounding causal effects. So they're willing to say, I don't want to impose implausible assumptions to get to a point. I'm rather willing to impose reasonable assumptions, but then I have to accept that I only get an interval for where the ostensibly true value is. So the idea here is that we can transform existing bounds in this framework and thereby immediately use a lot of existing results to bound the superoptimal regimes in the same way that we have done with optimal regimes. So you can build on a rich literature from computer science, for example, these bulky and Pearl bounds that I will touch on from the late 1990s, and also some results from econometrics and statistics on non-parametric bounds. And I haven't given you a lot of, intentionally not given you a lot of technical details here, but one of the key things is that our parameter of interest, which can be expressed in this way, is a monotone function of this simpler parameter that people have already bounded before. Okay. But one practical concern about bounds is that they very often are uninformative. Okay. And by uninformative, that means that they somehow cover the null effect. So you may have a lower bound that's below zero and an upper bound that's above zero, and suppose then you don't know, suppose they bound the contrast, so the causal effect, and you don't really know if the effect is positive or negative. And these are logical bounds, so you wouldn't get, you wouldn't get an interval outside of zero, even if the sample size was growing to infinity. Okay, so you may give up then and say we don't know what to do. Or you may say, well, there exist formal decision theoretic results for studying these kind of problems. And we still have to make some decisions. So if that's all the information we have, we better use it in the best possible ways. And just to back that up a little bit, I mean, I'm not saying it's trivial how to make decisions with bounds. And other people would not even do it. They would put priors on this and get into Bayesian decision theory. But one option is to use criteria such as the minimax regret, which appear a lot in economics, but you could also do other things. Some people, that's a matter of choice, but at least they can be consistent. They could be optimists. So essentially just choosing the option that leads to the highest upper bound on what the true effect is. You could be a pessimist. You could choose the one with the highest lower bound to minimize the lower bound. Or you could do something that FDA seemed pretty close to doing. So the drug approvers in the US, where they say, we would only choose a new treatment if we can guarantee that the worst possible outcome of the new treatment is better than the status quo, the current treatment. Okay? And all of these things can be implemented somehow with bounds as well. So let's see how we can use this as an example. So I'll go back to this Balke and Pearl paper from the late 1990s, where they introduced these kind of Balke and Pearl bounds, which are also for instrumental variable settings. And I'll use exactly their example. So this example from their paper concerns also a medical problem, although these are computer scientists, and it's about supplementing young children with vitamin A. So this study is from northern Sumatra, and more than 400 villages were randomly assigned to receiving vitamin A supplementation, which then could be given to mothers that could give this again to their children, or not receiving any supplementation. But of course, the fact that a village receives supplementation doesn't mean that, and even a mother receives a supplementation doesn't mean that the mother gives that supplementation to the kid. And even if they randomly assign the supplementation, the effect we're really interested in is what, and that's also Balke and Pearl's argument, what would happen if the mother gave the supplementation versus not. Okay, so this was a fairly large study because there are 450 villages and possibly thousands of individuals in each village. So Balky and Pearl didn't even bother with giving uncertainty estimates because apparently the standard errors were so small. But this is just a table of the results, not very interesting. What is interesting is that Balky and Pearl said we cannot, even if the villages were randomly assigned, we cannot really figuring out what the effect of actually taking the supplementation is. So they gave a bound for it. So there's their upper bound and the lower bound. Okay. But the interesting thing is if you use the superoptimal idea without adding any assumptions, you can actually point identify what the effect is in the subgroup of mothers who intentionally took vitamin A supplementation. So even without any assumptions here, adding any assumptions. Okay. The other question from Guillaume, I think. You want to raise that?
Yeah, sorry. I mean, I guess I've resolved it. I was a bit confused because I had the impression that you had cases where A was 1 and the patient had not received any vitamin A, but I see that the bottom row of the left table is 0, 0, probably because
exactly.
Of that reason.
And this is an important observation because that's actually precisely why I can point and identify it here, which means that if the village did not have any vitamin A supplementation, nobody could actually get it in that village. Whereas then, in the village where people had vitamin A supplementation, they could say no.
But then A is not really, does not correspond here to what would have been the intention of the mother had she had the choice. Right? No, so I mean, like, I don't know, I'm a bit confused because in your previous example, A corresponded to the decision, I mean, what you were considering was the natural decision that people would have made. Yep. Whereas here, it's a bit more complicated because in one of the two cases, you have the choice and in the other, you don't. Exactly. Is that a problem?
It is, broadly speaking, it isn't a problem. And in this setting, it turns out not to be, but I've swept it completely under the rug. So I could further condition on A equals 1 and set equals 1, which means that those who decided to take it when they actually had the option to take it. Does that make sense? So
yes,
I need to further condition on that because the A equals 1, I don't know who they are in the other arm, but it actually works because C is randomly assigned. So further conditioning on C equals 1 or 0 doesn't matter essentially. So this is why it should work.
Okay, great, thanks.
But you're completely right about that. So the interesting point about this is that even if a simple mean is not, or simple contrast in mean is not point identified, we may sometimes, and this is arguably, I was lucky and found a very good case for our own thing here, that where this one is still point identified. And people who know this game, they would also see, but this is just equal to the treatment effect among the treated, which is also a known quantity in econometrics. And that's true in this simple example, but it still illustrates the point that we can actually get something for free by just using a different identification strategy. And of course, we don't get an entire free lunch, as we never do. So if you look at the treatment effect among the untreated, we will get wider bounds. So all I can say with this is that Balky and Pearl came up with these bounds for a marginal quantity, but we can actually decompose those bounds into one point identified quantity and one other quantity, which is far from point identified. In fact, it's capturing all the uncertainty in the previous bounds. Okay. So to conclude, this work is motivated by the fact. Is motivated by the fact that there seems to be a tension between stakeholders accepting algorithmized decisions and making them based on existing expert knowledge. And it doesn't seem to be entirely clear when one should override the other and vice versa. And with this work, we somehow try, at least in a simple setting, to unify some of the ideas and figuring out how we could use the best from both camps. And if you look carefully at what I've done, only presented results in settings where we have one simple binary treatment, A is equal to 0 and A equals 1. And in fact, it becomes more difficult if it's a categorical treatment, or if you want a continuous treatment. It would not be trivial to do this. You would actually then need to work on bounds in even the more simpler settings. On the other hand, when we come to sequential problems, which I think are more common and often very interesting, where you make one decision and based on this decision, you make a new one later on, also when you have updated information and so forth, the same ideas should carry forward. They haven't done the theoretical work yet, but that's the direction to go. And the guarantees we have given, they're true in expectation. The fact that we have guarantees that are true in expectation doesn't mean that they hold in any finite sample analysis, or we cannot say that the estimators even perform in the same way as existing ones, but working on the estimation theory is certainly something we will do and already have done, but I haven't given you the details here today. So I'll end there and thank my group. And a lot of this work was done together with Aaron Sarvet, who's a postdoc in my group, and he's brilliant and will soon be on the job market.
It's the advantage of a physical meeting, actually.
Yeah.
Applaud.
Yeah, right, exactly.
Was missing. So let me
Thanks a
just
lot
say
for the
some.
talk.
Thank you.
Let me just say some words of closing for the seminar, please. So thank you once again, Mats. It was really great. And just be reminded the next seminars, next Monday, same time, same place. You have the opportunity to learn more about Bart de Planke's lab's activities. He's based in SV, but he's also associated to IBI. 8th of March, same week, we have the industry day. Feel free to pop by. We're going to be at the Swiss Tech from noon to 6 p.m. There's even an upper offer. You just have to sign up. Entry is free. We have a couple of demonstrations coming from the research pillars we've spun up over the last 3.5 years. And there's a roundtable on AI for engineering. So please feel free to come and participate. Then again, next week from 9 to 10 March, we're looking forward actually to welcome the colleagues from the Japanese RIKEN AIP. So this is the Japanese AI research, national research initiative. They come for a workshop. It's the first time they fly in. It's a 2-day event. It's free as well. It's at BM 5202. Look at our website, cs.epfl.ch, if you didn't get our newsletter today. And then last but not least, on 30th of March, we have our CS network seminar with Professor Olivier Michelin coming up. So he's a professor, he's a medical doctor at CHUV, and he's going to speak, I don't have the exact title in mind, but it's about precision medicine and how to use data science for treatment of patients. Thank you, goodbye.